Good morning, everyone. I'm Xiang, and I'm happy to be here with you to share my work for commit testing. As we all know, software vulnerabilities can pose a significant security threat. Thus, program testing is crucial. While within the thousands of lines of code that a program compromises, newly introduced code through commits can be critical. Recent studies have revealed that nearly 4 in 5 bugs in OSS fuzz are regression bugs, which means that the bugs are introduced by new commits. As the cartoon demonstrates, developers may introduce several new bugs when fixing one older bug. So, considering the high likelihood of newly added code introducing vulnerabilities, and the growing trend of program scale but limited availability of resources, it is crucial to prioritize fuzzing commit modified codes. To better understand the characteristics of commit-introduced bugs, we studied the recent closed issues of some projects reported on GitHub and GitLab, and manually identified bug-inducing commits of 30 real-world bugs. We then observed that first, the bug's crash sites often differs from the commit change site. Second, the bug-inducing commits often involve multiple change sites. It is straightforward for us to resort to directed fuzzing to solve target testing questions. And while there are some directed fuzzing works, including distance-based AlphaGo and reachability-based beacon, has shown great effectiveness in bug discovery, they still encounter several problems under the commit testing scenario. First, in commit testing, the targets of fuzzers are often set as the commit change site, while a single modified in the commit can significantly affect the entire program. The introduced bug can crash at a different site than the change site. However, existing works mainly focus on reaching the target as quickly as possible, but they neglect to thoroughly test the commit-affected code. So they may overlook some new bugs. Second, as the commit contains multiple change sites, the fuzzer has multiple targets. As the target's number increases, the directness of directed fuzzers may decrease. In the worst case, they may degrade to a coverage-based fuzzer. Although there are some fuzzers designed to solve multi-target scenarios, their targets are always sanitizer-marked locations, which disregard the connections between change sites. For example, some chains are within the same function, and then they will be less efficient. Therefore, if we want to efficiently uncover the new bugs commits introduces, we have to solve two challenges. First is how to quickly and thoroughly test the affected code, not only reaching the change site, but also test the affected code. The second one is how to handle the multiple targets in a smart and lightweight manner. To solve the first question, of course, like existing directed fuzzers, we have to first efficiently reach the change site. And once we reach the target or some critical code, we will try to maintain the reachabilities and generate diverse inputs to explore different program states of the affected code. For the second question, we will try to guarantee the directness for each grouped target, which I will explain in more detail later. Here is the overall architecture of our tool, AlphaGo. In short, this is a critical code-guided directed fuzzer for commit. For each commit, we will first extract the commit diff, and based on the code structure, we will group the original commit change sites to function-level targets. And then we will calculate the distance for each grouped seed individually. We also utilize program analysis techniques like tent analysis and control flow graph construction techniques to identify the critical code. And with them, we will use the critical code to guide the input generation strategy for the customized fuzzing. So to realize our goal, we have to first define and identify what the critical code is. Formally, we define two kinds of critical code, which are path prefix code and data surface code. As the name indicates, the path prefix code refers to the control flow prefixes that can affect the change site, and the data surface code represents the code that has data dependencies with the critical variables used in the change site. Here we present an illustration example where we assume there is a commit that changes line 14, and thus we set line 14 and basic block G as the target. Then the path prefix code is basic block A, B, E, and F, and the data surface code would be basic block I and K. Here, for the data surface code, to reduce the analysis workload, we only consider the critical variables. In other words, the variables that are written in the change sites are considered. So in the basic block G, there are two variables, X and Y. While X is written, we only track the code that have data dependencies with variable X, which are I and K, while block J and L are not data surface code. With the help of the static value flow analysis framework SVF, we can build the control flow graph and the data flow graph for more precise analysis. With the critical code, we proposed a new input generation strategy. The key insight here is that when we find a seed that executes some critical code, we want to preserve the execution of it while generating diverse test cases to explore the input space. In this example, if we found a seed A with execution trees A, B, E, F, M, which has not reached the target G yet, we will try to preserve the execution of edges related to the path prefix code, which are HEF, BE, and AB. Then if we found a seed B with trees A, B, E, G, I, J, L, which has already reached the target, we will try to preserve the execution edge of EG, BE, AB, and then surface edge GI. Here, after we found a seed that has already reached the target, we will still try to preserve the prefix edges because we want to balance the explorer width and depth and to avoid track into a local optimization with a fixed path prefix path. To preserve the execution specifically, we will generate a mutation mask for each seed. The mask will instruct the fuzzer to mutate those input bytes that will not deviate from the target and to sustain target edge execution. This is the key insight and design of our work. The new input generation strategy deals with challenge 1 to help mutate a seed to quickly reach the target and also helps to generate more diverse test cases to thoroughly test affected code after reach the target with the path prefix code and the data surface code. For the multi-target challenge, we have proposed a simple way to solve it. First, we will group the commit change sites based on the program structure, which is that if two change sites are within the same function, we will set the immediate dominant basic block as the grouped target. Then, to make sure every target gains enough attention to fuzz, we will calculate the input distance for the rearest executed target and assign energy for it. As we have grouped the targets from instruction level to function level, the size of the target is much smaller, and the cost of distance calculation is under control. And then we will move to the evaluation part. We have compared AlphaGo with 8 fuzzers on the effectiveness of bug reproducing, and AlphaGo successfully reproduced the most bugs with an average speed of 10 times. We also evaluated the age and path number AlphaGo and the baseline AlphaGo discovered during fuzzing. We can find that AlphaGo performs much better. As for the multi-target optimizations, compared to fish fuzz, a fuzzer designed for multi-target scenarios, we find the seed distribution of AlphaGo and fish fuzz is similar, while the baseline AlphaGo neglects target 0 and thus fail to reproduce the bug. For the real-world use, AlphaGo discovered 7 new bugs, and including 4 CVEs. That is all of my presentations. In total, we built a real-world data set and point out 2 characteristics commit introducing bugs have. We highlight the significance of thoroughly fuzzing the affected code in the context of commit testing, and we proposed a commit-directed Greybox fuzzer that utilized the novel critical code-guided input generation strategy. The experimental results also show AlphaGo is effective. If you have any other questions, you can point out and reach me through this email address. Thank you.